Oh, there you go. Okay.
Welcome, folks. We'll just give it another couple of minutes as people join the webinar, and then we'll get started. All right, well, thank you everyone for joining us today. We're going to be discussing the new LF connectivity project in today's webinar. Just a couple of housekeeping items before we introduce our panelists. You can ask questions during the webinar. There is a Q&A box towards the bottom of your screen. Feel free to type a question in anytime. We will try to dedicate some time at the end for open Q&A. And speakers may be able to address some of the questions in real time. It just sort of depends on the flow of each panelist presentation. This session is being recorded, so you'll be able to come back and watch it later. We'll make sure the recording gets published, and we'll promote the link to that, and we'll make sure everybody gets that sent via email. And all of our attendees will be muted during the presentation. So if you have a question, just shoot it in the Q&A box. All right, and here
full screen, Jill.
Yeah, sorry about that. All right, today's panelists, we have Arpit Joshipura with the Linux Foundation, Shah Raman with Meta, Kalyan Subramanian with Meta, Lakshmi Pradeep also with Meta, Paul Varkey with Meta, and Murali Raghunathan with Meta as well. Here's a quick agenda. Arpit and Shah are going to kick us off with an overview of LF connectivity before the rest of our panelists go into more details on each of the 3 sub-projects. All right, without further ado, Arpit and Shah.
All right, go for it.
Hi, everybody. Yeah, it's a wonderful morning and evening, afternoon to you all. And I'm very excited to be talking about and introducing the new umbrella project, which we have. We've been working on many of these projects for several years. Some go as long as 7 years, some as low as 3 years. And we are open sourcing those projects and bringing them together with Linux Foundation in partnership with them as an entity called the Linux Foundation Connectivity. And let me just start off by laying out the vision for this new umbrella project, and kind of like lay out why do we believe that this is an important mission or a vision that we should the industry should look at and consider participating and contributing. So we're going to keep things at the high level for this project as this session, because this is the very first one. And then we'll likely have follow-up sessions as Linux Foundation Connectivity starts coming together and forming in the early days. And I'm very delighted to be doing this with it just feels like several Meta folks, because the projects that we're going with on the onset are really the ones that we've been working on at the group called the Meta Connectivity. And you'll hear more about some of the high-level overview, architecture, use cases, and things like that from the specific projects. And Arpit and I are going to talk about more at the LF connectivity level. So, starting with the vision, if you look at what are we looking at is to really try and build a sustainable ecosystem around building the open source. I think these are the key points I've underscored here. Really, the sustainable ecosystem, number one. Number two is that this is all about open source tools and technologies. How do we kind of have a thriving and ecosystem of open source tools and technologies that help us advance and the enhanced last mile access? And we know this is a struggle. This has been a struggle for a very long time. Half the global population are still not online, and there's and those who are online, many of them do not have the kind of I would say the connection speed, the latency that's required, the kind of quality of service that's required in order to support that. You just list out, these are some of the example scenarios. Like if you're like in a very dense urban situation, you got a lot of congestion happening. If you're in a rural situation, you sometimes have lack of the broadband speed connectivity. And then we have the emerging AI, AR, VR, these applications are coming up. So this continues to be a problem. And so we really want to see how do we build a sustainable ecosystem with open source tools and technologies and towards the enhanced last mile access. And this builds on top of a lot of the work that we've done at Meta over the years. And it's my great pleasure to have this now in partnership with Linux Foundation as an open ecosystem called Linux Foundation Connectivity. Okay, so let's move to the next slide, please. Yeah, so with that vision in mind, I'm just going to quickly cover the challenges that we have in these, and these are by no means an exhaustive list, or even like I would say the highest priority list either. But these are some of the key challenges that we faced through years of research, through years of working in the connectivity space, and there's a lot of work that's been that has happened to advance these. There's a lot of standards and a lot of open source software as well in the core space, cloud, and some of the telecom focused access technologies. But there are definitely some of the special cases or these upcoming cases in the last mile access that continue to require target solutions is what our hypothesis is. And then if we think about things like the dense urban or really rural access that you can provide through the high frequencies, especially in the millimeter wave, the free millimeter wave space, not the license part of it. That's kind of like, how do you really leverage that? And then finally, there's quite a bit of a challenge, I would say, in terms of doing the coverage and capacity design that leverages the emerging technologies such as deeper programmability or AI ML technologies. So these are sort of like the three spaces, what I would say, that we have looked at, and I think this is some of the just some of the challenges that we're aware of. Next slide, please. So this is just an announcement, and Arpit, do you want to talk about this?
Yeah, let's.
Please.
Thanks, Shah. So, given the need for enhanced access, and again, for those of you on the call, there's the core, there's the edge, and then there's the access, right? And then for the standard access, which is telecom service providers, the 5G mobile broadband, we got some decent coverage and all that. But then, what about the dense? What about the rural? And then what about high density, and what about AI ML and all these things we need to do to make it even better, right? That's the connectivity umbrella. And our goal here, it's an umbrella at the same level under the Linux Foundation as LF networking, LF Edge, CNCF, etc. So it is a group of what I call sub-foundation projects, and we are really excited to have launched this and announced this last month. We're already seeing a lot of interest in this from several of our partners and contributors. And today we are going to have the experts on the first 3 projects that have been announced as part of this, and a lot more coming. They will talk about the use case and the deployment and what it is about, right? Some of these projects have been deployed, and there are some excellent videos on the website that will show you the scale and the impact of these projects. So if you go to the next slide, we recognize that there's a set of partners that have been working on this, and we are really excited to just keep growing the ecosystem on this. But what I wanted to focus on in the next slide is really around how it fits with the rest of all the work that's going on in the Linux Foundation. So if you go to the next slide, Jill. All right. So this is one of the more common diagrams I always use. But if an end user says, I need to build everything or as much as possible using open source building blocks and projects, this is a fairly straightforward architecture where you have the access, and whether it's mobile access, residential, small, medium business, enterprise with data centers coming in through 2 types of edges, user edge, service provider edge, into some version of a cloud up on the right through public clouds into the stack with NOSes like Sonic and Dent, data plane technologies that accelerate like FDIO, DPDK, up into the stack with controllers, Open Daylight, orchestrators, ONAP, and then applications, all the way to mobile packet core where Magma fits in. And then on some of the enterprise side of applications, you have Leaf, which is a Walmart type project with eBPF going all the way down. But the reason I want to put this slide up is now we have, I wouldn't say completed our vision and journey that we started 5 years ago, where telecom was always, and networking was always kind of proprietary. And then the service providers led the revolution of making it open source so that quicker, faster, better innovation can happen. And so we introduced this LF networking, we introduced LF Edge, and now LF connectivity, which really helps the last mile enhanced access across mobile, residential, and SMB. And you can see the O-RAN Alliance part of it, which is the standard access for service providers, is already as a complementary. So it fills in the whole picture. And I don't want to spend too much time on these projects, but I wanted to give you the perspective of how the end-to-end open source networking system is built. Okay, with that, Shah, back to you on the governance and introduction on the projects.
Yeah, great. So I think what RP just shared is a great way to look at this, looking at the end-to-end, the holistic picture, which is really, really important, because you may be wondering about that, right? We have LF networking, we have LF Edge. What is going to be the role of LF connectivity, and why do we need another project? So thank you for that articulation. And I just building on that, as you saw in that picture, that there's a lot of coverage, but when you actually look at the access side of it, at least from an open source perspective, we always felt that there is a gap there, there's a hole there, and one of the great ways to think about that hole, or as you think about like filling that hole, is one of these projects here that what we've worked on at Meta for over 7 years. It's called the Terragraph. So before I go into the details of that, and we have Lakshmi with us, like who's really worked on this probably over 5 years, to we'll share more details. But let me just lay out a little bit of like how we thought about the LF connectivity and some of the principles that we felt are super important right on the onset. Is that the first of all, we don't mean to make this a heavyweight open source project. And by heavyweight, I simply mean there's like in some of the projects that you have are large and complex, and you have governing board, you have a technical steering committee, you have outreach committee, you have like many other aspects and pieces to pull the projects together. We wanted to keep LF connectivity very, very lightweight. And to go with that, the concept is to really have a simple advisory board. We're looking at roughly between 2 and 5 people. Right now we have only 2 people. It's me and Shadi Hassan are going to be on this, and I'd love to have had Shadi on the call. He was not able to attend, but I'm sure in future sessions that he will be with me here and others. So right now it's just Shadi and myself. We're going to be on the advisory board, and it's a very lightweight oversight for the entire umbrella project that we intend to have, and it's going to keep it light in that manner. And then as you come within LF connectivity, the different projects that within LF connectivity that we'll have, and 3 just a starting point. These 3 are the seed projects, what we're calling the seed projects, and each of them are going to have their own technical steering committee. And over time, if we see a need for having the functions, so there'll be like a little bit of the second principle, I would say, is that like functional split or sort of like the governance split, if you will, which is going to be, again, very, very lightweight. At the LF connectivity level, we will decide from the advisory board and maybe a rep from the TSC that where does a specific function fall, and where, we may do certain things such as maybe talk about LF connectivity and promote those at the LF connectivity level, and that would probably sit with LF connectivity. And we also have, we will have a LF connectivity level coordinator, Somsigar, who's been really the trooper. Sometimes not I won't call the unsung hero, but more like the someone who doesn't get enough mentions, at least. So he's the one who's really done a lot of work with the amazing LF team to pull this all together. He'll continue to be the project coordinator for LF connectivity. at that level, right? So that's pretty much it. It's a very simple structure. And each project will have the TSC, and then they would be pretty much running the sub project would have the TSC, and they'll be running it pretty much, I would say, as independently and as autonomously as possible. Okay, that's sort of like the kind of the thinking process at this point. We have the 3 projects to begin with, and each of those have already sort of that's the third principle is the TSC, the Technical Steering Committee. The idea is to have the Technical Steering Committee to be as represented as possible from the people within the project, or contributors, maintainers, or have some very strong relationship if they're not right at the code level. And they would sort of be from that Technical Steering Committee and drive the go forward vision, roadmap, and so on for the specific project. Okay, and we welcome your participation. Please reach out to us, because these TSCs are not all formed at this point, and we want to invite people from the community to actually join if you care and you'd like to contribute and you'd like to participate, right? So I think that's sort of like the 3 things I wanted to lay out. And then so just a couple of words about these 3 projects, and then I'll hand over to Kalyan to start with the Terragraph, providing the overview on that specific project. So Terragraph, as I was alluding earlier, is the 60 gigahertz millimeter wave. The mostly operates. It's a radio-based product or platform. It has many different pieces, but it works basically in the 60 gigahertz unlicensed millimeter space, and then it is able to deliver connection speeds all the way to I wouldn't say the upper limit, but in the gigabits per second range. So it's a very, very it's not a long distance wireless solution, but it's a very, very powerful last mile access solution that can deliver, especially when you think about the AR/VR AI type use cases. It can deliver lots of data at lower latency for the last mile. Okay. Then we have the open M plane. This is probably going to be a great complement to the Open RAN or the ORAN movement in general, and there is a need for having an M plane that has a greatly laid out HAL layer, like abstracting all the different radio nuances, greatly laid out integration into the ORAN components, whether it's RU, DU, CU, and then sort of like have client server architecture to be able to manage that entire thing. And we're open sourcing this, so I think this is I'd like to call out to the OSC, the ORAN software community, who might be able to benefit from this open source M plane, so that many of the radio vendors or ORAN product vendors won't have to reinvent or do the M plane part, because sometimes it's looked at it at the very end, and it can actually be a complicated affair to actually build one. So this is where the value of open M plane come in, so you can really lay out, kind of deploy these radios very easily, manage them very easily, and so on. And finally, last but not the least, quick word about Maverick. This is what I'll say is probably the newest of the 3 projects, yet probably the most powerful one, because it has I would say AI/ML engine that's actually is much needed for the industry. And this is probably the one that will not only focus on the last mile access, but it probably has a broader applicability. I will let Murli and Paul to expand on that, because it's a really, really powerful platform. And I'm very excited to see this sort of like becoming open source with the LF connectivity, because we believe there's many of you are attending, and widely the community can take advantage of that. Okay, so with that, as it says here, the next few months we are going to work on forming those TSCs, and we're going to also we have a few more projects in the pipeline, at least 2 to 3 that we can think of. So for the rest of the year, we're going to focus on formation of the project overall. Okay, so with that, let me hand over to Kalyan Subramanian. Thank you so much, Kal.
Great. Hi, folks. Lakshmi, do you want to?
I'm sorry.
Or I can go either.
Yeah.
Sorry,
I'm sorry. It's my bad. It's actually should be Lakshmi doing the Terragraph. I mean, both of them worked on Terragraph for so long. I had my wires mixed up a little bit.
All good. It's all good.
Can we go to the previous slide, Ajay? Thank you so much. So let me begin with a statistic and the motivation of building this Terragraph. So ITU estimated about 37% of the world's population, or about 2.7 billion people, have still never ever used the internet. This was in November 2021, well into COVID days, where we are forced to use the internet for everything, be it work related, getting news, health updates, government services, etc. Even our kids had to glue to computers to get their education. People found many ways to connect, but why are still so many left behind? We don't need to look further. The key reason being no affordable infrastructure. The ISPs are often faced with limited options to offer reliable gigabit broadband services. Either they like costly fiber or install wireless technologies, and can be unreliable and difficult to ask. So this led us to ask the question: how to bring more people online to faster internet, more importantly, without breaking your bank or back. Else also evolved from our mission statement, connecting the unconnected. Eventually, this drew us to build Terragraph. Before diving further, this is Lakshmi. I'm one of the founding engineers of the Terragraph. I was involved from very early days of identifying silicon vendors, involved in low-level software firmware development, troubleshooting problems from deployment, and eventually landed the protocol into IEEE standards. So let's move to the next slide, Jill. So next slide, please. So what is Terragraph? I'll be referring Terragraph as TG. So TG is basically a multi-node wireless software-defined network, and then operates in an unlicensed band, as Shah mentioned, in 60 gigahertz spectrum. It's mostly unlicensed. I say mostly because some countries do have some licensing around it. It's also, Terragraph is a distribution level network designed to augment and expand the fiber optic network. It enables high-speed connectivity in particularly in multiple environments, specifically urban dense environments. When combined with fixed access connections or Wi-Fi access point, Terragraph is a low-cost solution to achieve street-level coverage. The industrial design allows for a quick and affordable deployments across many markets. In essence, you can say Terragraph is a wireless fiber. So the ecosystem components incorporates commercial off-the-shelf components, including a leading silicon supplier, advanced antenna module vendors, and several OEMs, and including partners such as Edge Core Networks, Ciclu, Cambium, Capgemini, etc. They offer hardware products and related services powered by Terragraph. It is to be noted that Cambium has largest operating commercial deployment. This project we started in 2015, and there are multitude of connectivity service providers worldwide who have adopted Terragraph. To name a few, YTL Communications at Malaysia and Deutsche Telekom and its subsidiary have deployed TG in various towns in Hungary. So the open source software stack at a high level, you have the kernel drivers, user space components, cloud software, and a network management system, and a millimeter wave network planner. This will get you off the ground in no time. Next slide, please. So let's see what constitutes the network elements. The Terragraph network is composed of individual nodes. They're supported by network services which are operating in the clouds. There are two types of cloud nodes. We call them as distribution node or a DN, or a client node or a CN. The DNs are the backbone of the Terragraph network and distribute internet connectivity from one or more fiber pops or multiple hops to CN. The DNs and CNs are connection points to the client networks, wireless access points, and other CPE to connect to the internet. So I'll move to the next slide. Yeah. So I want to understand this node architecture. Let's look into some functional blocks. Each node in the Terragraph network is a layer 3 router, and the nodes route traffic within and between the Terragraph network and also attached access networks using routing information provided by Open Routing Protocol. It's commonly called as OpenR, and it's Meta's internally designed developed interior routing platform. OpenR was originally designed and built for performing routing on Terragraph mesh network. Its flexible design has led to its adoption in other networks, including Meta's new WAN network or Express backbone, etc. Please refer to this OpenR's GitHub page. It contains plenty of examples to leverage from. So finally, the over-the-air link protocol between the nodes uses a modified version of 822.11ad and a significantly slimmed down version of the MAC layer. The MAC layer is modified to use a scheduled MAC instead of a contention MAC, thereby making airtime efficient. This TG operates in CDD TDMA mode. In addition, each node comes with a multi-element phased array antenna, and that uses advanced beamforming techniques. Using these beamforming techniques, we are able to form high-quality communication links with line of sight and reflection paths. The distance between the nodes can exceed anywhere about 250 meters. The TG links also uses GPS for time synchronization, and it is used as one of the methods to mitigate the co-channel interference. The data path, if you observe here, data path is implemented using DPDK and services such as traffic classifier, HQS, routing, etc., built over VPP. The framework provides flexibility to add or modify or add new services with much ease. Besides this, besides these core blocks, the node contains exhaustive infrastructure elements such as logging, statistics, etc., for easy deployment, debugging, and system analysis. Can we move to the next slide? So going up the software stack, the TG utilizes cloud to service two critical services. That's the end-to-end service and the network management service. This slide captures actually a comprehensive list of all services that are part of the cloud suite. The cloud suite is typically deployed as Docker services in a Docker Swarm. The end-to-end services provide a minimum functionality to bring up and run the Terragraph network. You can see the key services are the end-to-end controller, API services, stats agent, NMS aggregator. So I'll just briefly give you an overview of these services. The end-to-end control is a software application. It primarily provides services that require network topology awareness and bring up of the wireless link, and additionally software upgrades and configuration management. The API service provides and exposes an HTTP interface to the end-to-end controller. These requests are translated into asynchronous thrift serialized 0MQ messages, and the responses are returned in plain JSON. So I think this is an interesting aspect which you can develop. You can develop your own mobile app too. We'll come to that in the next towards the end. Then there is another service called stats agent, and that's the agent collecting various system stats from the controller host. Sorry, the next slide. Go down further. The next slide. Yeah, I'm still on the next slide. Yes. The NMS aggregator is an aggregator that collects raw statistics from the agent that's running on the nodes. It computes the counter values and sends to the query service to store the data in a Prometheus backend. This can be configured to send the computed values to other HTTP nodes. Yes. So we can move to the next slide. So it is all about NMS. Before I talk about the slide, I want to just give you 2 lines overview of what our NMS does. The Terragraph network management is designed to help operators and developers manage the network. Nearly all operations in the NMS are commands sent directly to the end-to-end controller. This NMS can connect to multiple end-to-end controllers, serving as a central platform for managing several Terragraph networks. The NMS backend encompasses all services concerned with data collection, visualizing, monitoring, and analysis of the network. So this slide is from one of the NMS UI showing the map view. The map view shows the status in that network according to an end-to-end controller. If you want to view the details of a specific sector, link, or a site, you can select the item of interest in the map, and you can view the details in a table form. Next slide, please. There are other additional software tools that we have open sourced to the community, namely millimeter network planner and a network test framework. This network planner is also commonly called as TG planner, and determines whether there is a valid line of sight between two sites. It allows operators to plan and optimize your mesh network using a combination of geographical information such as clutter, terrain, and the hardware capability. That's the hardware information about the nodes. This planner provides 2 approaches of modeling the propagation of radio waves to determine whether there is an obstruction or not. It's simply one is a simple cylindrical model, the other one is an accurate ellipsoidal model. So the next software tool is the connectivity test frame. It's an automated test suite for Terragraph consisting of test implementation and test runner application. It can also be used as a CI/CD tool for managing any of your future software development cycles. Please refer to the repo and the manuals provided in these pages for more details. Can I go to the next page? So here is a common cases and deployment scenarios. One is a fixed wireless sorry, the fixed wireless provides basically connectivity to single family homes or multi-dwelling and etc. There is another second use case is Wi-Fi metropolitan coverage. Suppose you want to cover a city like San Jose and provide services in a park and things like that, or even in a university where you want to provide coverage, it can be augmented with Wi-Fi. Thirdly, the third use case is a mobile backhaul. Usually, the new generation cellular networks requires really dense deployment and multi-gigabit data rates to backhaul the radio sites. And where you cannot, fiber is not possible, or the mobile backhaul is not possible, you can use Terragraph as an augmenting to this capacity, to augment capacities in areas where it is not viable. And that's about it at a high level. I would like to conclude by highlighting TG's performance and advantages of this open source software capabilities. The TG Link supports up to 4 gigabits per second bidirectional and up to 15 hops. Having mentioned this metric, this open source software provides a great competitive edge and includes all you need to deploy immediately, and also the necessary software API and hooks to scale up for your future needs. It's a great place to begin your TG journey. And finally, thank you. Thanks to everybody for listening and this opportunity to talk about TG. Next to you, Kalyan.
Great. That's awesome. Thank you, Lakshmi. And thanks, Arpit and Shah, Som, and everybody for getting us this far. This is really a thrilling conclusion to the work that I started on about 3 years ago at Facebook and now at Meta. And thanks everybody for attending this webinar. The Open M plane, as it's called here, is basically a short form for an open source management plane. The M, of course, stands for management. Management of what? It's management of Open RAN compliant radios. And those of you that come from the telecom part of the universe might already know what the acronyms here mean. If you don't, please feel free to Google them. I mean, that's the quickest way to get to know that as we go along this talk. I'm happy to take questions offline. So thank you, Jill, for getting us to the next slide quickly. This is basically a high-level overview of what this is. Like I described earlier, the contribution that we're making to the Linux Foundation today is an open source implementation of the management plane software component. We launched this as part of a larger umbrella program within Facebook back in the day called EvenStar. EvenStar's mission was to sort of democratize access to radios, which are Open RAN compliant, as well as the distributed units, which would kind of be the complementary node to the radio in the open radio access network. And the part that this software plays in that system is essentially the FCAPS functionality. Those of you from the telecom part of the universe might recognize that acronym. FCAPS is basically the management of fault, configuration, authentication, performance, and security. So all these 5 dimensions are provided by the management plane software component. And the key distinction here is there's a lot of open source FCAPS components that you can kind of deploy. This was kind of organically grown from the ORAN specs, which means if you already have an ORAN compliant design that your radio unit provides, as a radio vendor, you have a tremendous advantage that you could go, deploy this right away on your ORAN compliant radio and not have to worry about, hey, how do I write the middle layer of software that lies above my firmware that then talks to a network management system, whether that management system resides on the distributed unit or it's basically an agent somewhere in the cloud, as most modern systems are, right? So it kind of takes the burden of heavy software R&D away from incumbent radio vendors as well as emerging radio players who generally have a high barrier to entry from the software R&D perspective to get into this market. So that's literally the value add. If you take one thing away from this presentation, that's literally what that is, right? Again, reiterating the previous point, we started this effort back at Facebook then and Meta now to support the ORAN Alliance industry standard, which was published way back. Our goal was to enable not only 5G, but then be backwards compatible with LTE as well. And then we started with the open front hall interface, which is specified by workgroup 4 of the ORAN spec, and that's literally what this implements. The way the configuration works is the configuration is programmatically described in a high-level human-readable language called Yang. Yang is pretty well known to people working in the network industry. It comes, I think there's an IETF RFC. Shah may have even worked on it back in the days at Cisco, and people that come from the networking industry that deal with switches and routers know this really well. So again, the point of all this is everything here is built with plain vanilla, readily available, easily understandable open source ingredients. So there's literally zero IP in this, except for one little critical part, which is no longer our IP. In that sense, we've open sourced it. So it's literally all open, and it's fully in the hands of anyone that can write software. Okay, so the way we designed this is basically a hardware abstraction layer, which I think Shah also initially referred to. That's the key innovation here. And I'm glad to say that the people that worked on it are on this call. Lakshmi was one of the people that worked with me on this. So we had this basic problem where you have a bunch of different radios, and each one of the radios have their own specific architecture. But back in the day, we weren't building our own radio, so we wanted to get a bunch of garden variety radios and see, can we write software on this and have it configured and talk to from external sources. So we found that we were repeating the same operations again and again on 2 different radios, for instance, and those operations really depended on the specific nature of the hardware implementation. By that I mean, was the hardware running on a ARM processor or like another embedded processor, maybe partly in the FPGA? How was register access managed? So there were a lot of low-level details which had to be kind of abstracted out in order to make the middle layer sort of common. Otherwise, you have to kind of rewrite it for every single instance. And then, as any software engineer knows, that's a bad design paradigm, right? So the basic idea of the HAL was to provide this sort of portability across different hardware platforms. And with that objective in mind, next slide, please. Thank you. So this is the architecture we came up with. So if you kind of look at the middle box here that says ORU, that's the Open RAN compliant radio unit. Like I said, the lowest rectangle there represents the firmware in purple. And our sort of little add-on on top of that sandwich was HAL. And that's essentially our contribution, which is completely open sourced. And now the HAL essentially is a set of APIs that you can easily hook into, given a certain radio configuration. And then you can write your own apps on top of it, or you can run our standard M-plane server component, which is on the right-hand side in this rectangle here. The M-plane server, again, it sounds fancy. It's pretty simple. It's really an SSH server that's sitting there, opens a socket, listens for incoming connections, and serves packets over SSH, right? And that addresses the security part. If you guys remember, we talked about FCAPs in the first slide. So that's the security aspect. And of course, we didn't have to reinvent everything from scratch. There's a consortium of Czech universities that's deployed this thing called NetOpere 2. It's an open source, fully Linux compliant package that you can download onto any embedded system. It's fully written in C and C++. Really lightweight, super fast, simple server, right? And then we also leverage sysrepo, which is another key open source contribution, again, by a variety of people, all under the standard Linux umbrella. So any embedded system that runs embedded Linux can host these bits and pieces, right? And all we've done is pretty much glue them together with this little magic called the HAL, right? And sysrepo, again, I wanted to call that out. It's really an embedded database. This embedded database is extremely flexible and powerful. You can enable and disable as many modules you want. It has all the standard asset properties of any large database system that you might be used to. So the usage from a query and setup kind of a perspective is super easy. If you're used to running even large scale databases, you'll find this a breeze. So using all this now, this needs to go talk to the outside world, right? So remember I said, You can either have a management system running on a distributed unit, which is classically the base station in the old architecture for LTE. And in 5G, it's now called a distributed unit. Anyway, it's something distinct from the radio, right? And then the other situation could be that you already have a network management system that's already managing a bunch of different entities. And this O-RAN radio unit just happens to be one of them. And that's typically how large operators deploy their systems. So in either case, the language, the protocol that goes from the radio to these management entities is exactly the same. Again, you'll be relieved to know we didn't invent anything here. This is an IETF RFC that's more than 20 years old called NetConf. So NetConf and Yang are kind of hand in hand, right? So both come from Cisco. It's been open sourced by many, many brilliant people. We just leverage that. And that's exactly what this does. So that's pretty much the software architecture here. It's extremely simple. Built entirely of open source ingredients that you can find in any Linux distribution, and out of the box you can get it running on your radio. I don't know, Lakshmi can jump in here. Lakshmi, how long did it take when we got a new board? Was it like a month, or I remember we had it up and running, right?
Exactly. I mean, there are two aspects of bringing up this whole HAL plane did not take us more than 2-3 weeks, but then the actual hardware and thing that was, of course, outside the scope of this one. But that is it really depends on the hardware. That only took time. But this piece was like the cake. Just put it there, and it works so seamlessly without any issues. Remember that we had to test this with multiple flavors of multiple radio vendors.
Exactly.
I can't remember this. So in each and every case, it was very simple.
Exactly. So I think that the key point here, folks, thanks, Lakshmi. The key point here is the HAL is a ready to go ingredient that you don't have to reinvent every time, right? So as long as you have your basic firmware up and running, hooking up those APIs is a breeze. Next slide, please. So I'll stop here. So this is like a really complex looking diagram, but essentially this is where does this component fit in? If you look at this picture, the last but one orange rectangle that says ORU, that's the Open RAN radio unit again. That talks to the ODU over what's called the Open Fronthaul M plane. That's the dark line here, the black line. And then there's also a black line from there all the way up to the service management and orchestration framework, often referred to as the SMO. Now my colleagues, Paul and Murali will probably talk about the non-real-time RIC. That'll kind of get into more of the other ingredients in this picture. So I'll have to turn it over to them. And I'm happy to take questions. And this again is really, I believe, our gift to the radio vendor ecosystem and the Linux community at large. We invite you to participate, hack, have fun with this. Thank you very much. Over to Murali and Paul.
Yeah, thanks, Kalyan. This is Murali Ranganathan. I'm jointly presenting the Maverick portion of this presentation with Paul Warkey. Next slide, please. Thanks, Kalyan, for setting up the O-RAN architecture and placing the component that we're familiar with and working with here on the Maverick project. Maverick stands for ML-Assisted Virtualized Efficient RIC, and the RIC in the name stands for RIC, as in the RAN Intelligent Controller. That's defined by O-RAN Alliance. There are two flavors of RIC for those of you that are familiar with it. There's a non-real-time RIC that Kalyan alluded to that's within the SMO, and there's a near real-time RIC that has interfaces towards the ODU and the OCU for more near real-time control of CU and DU functions. The motivation for us to build the Maverick project was to, as the name suggests, was to make the RIC development aspect more efficient and bring in ML components to enhance radio optimization solutions that would run on the RIC. Typically, what we expect to run on RIC as apps, they call them in the O-RAN Alliance as XApps that run on the near real-time RIC and R apps that run on the non-real-time RIC. These apps truly make Open RAN, I would say, truly open from that context, because third parties can now build these XApps and R apps and then run those apps to perform various functions. Could be optimization functions, could be configuration functions, could be just management of the layer 3, layer 2 functionality on the CU and DU, just extension of call processing if you want to make the RIC really an integral part of the CU and DU operations in an O-RAN architecture. So our goal was to create these ML algorithms that would allow an engineer who's creating these XApps and R apps to test their applications in a test platform, in a emulation platform, without having to go to a real network. Given that these optimization algorithms need real traffic, real mobility, coverage and capacity aspects of real networks with users, but it's hard for third-party application developers to go to an operator, find the right environment to test against in order to prove the value of these XApps and RApps and optimization solutions they bring in. And that was a huge problem for the industry on how to make the RIC a powerful ingredient in the ORAN architecture, at the same time enable third parties to easily build and validate and prove their solutions in an environment that represents a real operator's network. And that's exactly the problem we're solving here. We're leveraging AI/ML to learn from actual network data. So we would have to work with operators to get their data and build models that represent that particular network. And once that model is learned, it can be brought into a lab environment where a RIC platform is set up to run the applications, or a emulation platform. One of the examples is a RIC test platform that Viavi produces. And Viavi is one of the partners that we worked with very closely to take the technology into their platform. And they'll also be part of our steering committee as we go forward here to enhance the capabilities of our solution. So in short, what we do is work with commercial operators, understand the data, and bring these models into lab platforms, integrate them into a RIC or into a RIC test environment. And then by doing so, third parties can build apps and test their apps and prove their apps in a lab with full confidence that what they've tested in a lab will provide the same value and benefit when run in a operator's network. Also, as the software stacks, both CU, DU, RIC, and other functions become more and more virtualized, we will find that these software stacks follow a CI/CD continuous testing model, where we want to push these software stacks into the operational network in a continuous fashion. And to do that, you'll have to evaluate and prove the software under different environments. And Maverick allows you to do that because we've now brought in representations of real networks into a lab. So CI/CD tools can test in a realistic environment before those apps are pushed into the network. So what we would be, and Paul is going to talk more about the architecture and the actual software models and how it's built and how it's used. But in closing, I'll mention that our contributions are going to include both prototypes of the models as well as example applications that use those prototypes. So with that, I'll pass on to Paul for covering the remaining slides. Thank you.
Thank you, Murali. Next slide, please. So yeah, so as Murali mentioned, the Maverick project, the core offering here is shown in the box on below, where we stated RIC algorithm development platform. And so that's essentially what we are offering to the community is a developer kit. And a core part of this developer kit is what is known as the digital twin or digital twins, which are ML, regression or supervised learning type models. And again, it's worth emphasizing for the developer community here that all of this is built on open source stack, right? PyTorch, gPyTorch, etc. And what the digital twin provides is a way of using the large amounts of data that network operators, potentially vendors, have access to train and create representations of their networks, whether that is the RF propagation aspects, or whether that is the user mobility or traffic and load scenario aspects. And then further, these trained models can be used to then generate metrics that are relevant to the various problems that Murali alluded to. We talk of non-real-time control problems, such as coverage and capacity optimization or energy savings. We could also talk about near real-time problems, which require a higher cadence of response, such as mobility, robustness optimization, or load balancing. And all of that is shown in the gray box above. So that's where we expect that these RIC developers or XApp, RApp developers will be active in the sense that they will try out different algorithms that hit these use cases. They use RADP and the digital twins within to evaluate sort of in a lab and development environment how the various solutions, and these solutions are going to be providing policies that configure or reconfigure various RRM type parameters on the network. And this developer kit enables them to evaluate these policies and these changes in a way, in an offline manner that doesn't have to intervene in the network. So that's the entire sort of the high level picture. Next slide, please. So this here picture is just trying to emphasize the workflow. I'll just sort of quickly go through this. And a typical workflow here, I want to emphasize again that the primary use case is sort of in a lab environment for the developers to build these apps and try out and evaluate these apps. So typically what's going to happen is from the network, we receive sort of the infrastructure topological configurations, as well as sort of these KPIs or the UE collected metrics. And these need not be provided real time. They could be sort of collected and provided in bulk. The twin is then realized again as a sort of a Docker service. That's what we have now released open source that can be continuously trained in sort of different episodes of training. And then it becomes available for this, what points 4, 5, and 6 are trying to show is how are the XApps and RApps leveraging the twin. It sort of provides these hypothetical configurations and queries the twin for the results. What are the hypothetical results of potential changes? And then this can be done in a loop and evaluated in a clever way before the actual sort of a configuration change is suggested back to the network. Next slide, please. And this again is sort of emphasizing that the initial use case here will focus on a lab deployment or a developer environment type scenario. But at some point, one may even envision that the digital twin could be realized and could exist as a kernel RApp on a RIC itself. So in order to support live optimization scenarios. That's sort of a future envisioned use case. We invite the community to participate, to hack with us, and to take this forward. But this is sort of the vision that we're excited about. And again, thank you all for listening. I think this concludes the technical portion of the presentation, and the panelists are happy to now move into the Q&A session.
Awesome.
Great. Thank you. Yeah, go ahead, Shah.
Yeah, I was just going to say that this is, like I was describing earlier, that this is probably, there's a lot of things here at Maverick for the community to look into. There's just so much. It's a development platform, probably an ideal thing for a community at LF for this. And just a quick comment on the M-plane. I think that's, Kalyan said it nicely, that this is a gift to the community. Just consider all of these projects as gifts to the community. We really want to see like an open ecosystem, hopefully with partners and building around them. So yeah, that's all. Yeah, back to you, Jill.
Great. It looks like we had a couple of questions in the window that were answered already by you, Shah, so thank you. We do have another question asking where we can get the recording. This will be published on YouTube to the LF Networking YouTube channel once the recording is available. And then we have a couple of other questions in just a few minutes, so let's see if we can get those addressed. Is Terragraph reflecting the 3GPP standards for all the target environment?
Yeah, any of us can take this, but Lakshmi, feel free.
Yes, sure. At this moment, Terragraph is not part of 3GPP. The current implementation is in a kind of initial version, so it was kind of proprietary, but now we have already pushed all the protocol, everything into IEEE standards 802.11 AY. So if you take 802.11 AY protocols, so that is Terragraph inside that.
Yeah, and just to add to that, I think it's probably important to distinguish the two. The 3GPP predominantly are license spectrum, right? You're looking at mobile operators, you're looking at providing services like 4G, 5G, what have you. And whereas Terragraph is really focused on the unlicensed millimeter wave, right? So there's really not a relevance from a 3GPP perspective. It's a lot more to the, on the Wi-Fi, if you will, then therefore the IEEE standards that Lakshmi described is the Wi-Fi standard.
Yeah. Thanks for lighting that.
Great, thank you. We did have another, oh, you have your hand up, Colligan?
Yeah, I just wanted to add, I don't know who asked the question, but there was a sort of a movement in the 3GPP community to integrate backhaul and access. There is a specification known as IAB. Shah's grinning. We kind of dabbled at that a while back, but I don't think it really got much more traction than a white paper from some of the big guys that you normally know. So if someone's interested in hacking on that, that would be a cool project. Just wanted to throw that out there.
There you go. You already have a potential project to consider.
Great, it looks like we got one more question that just came in about Maverick. RAN data that feeds the different models are also available, question mark, or does the community need to work with operators? How are new 5G features handled for which data may not be there?
Yeah, I can answer live. Yeah, so we ship the models with examples that do not include, of course, actual operated data, which are private to them. But these examples include sort of dummy realizations of what the data could look like. One of the ways we envision Maverick would be useful in the context of this question is it can even support tight, closed trials. If a third party, vendor, or otherwise wants to collaborate with operators and evaluate solutions, Maverick supports that, even if that happens to be sort of a closed environment. Yeah.
Okay, well, it looks like there are no more questions, and we've just got a couple more minutes unless any of our speakers have anything else they'd like to add. I think we can close for today.
Yeah, I think you might want to put up the
Yeah.
website, Jill. Last slide. There you go. So feel free to look at it, browse through the links, the videos, and participate in the TSCs as they get formed and started. Thank you very much for this exciting panelist, and we really appreciate all the questions. So thank you.
Yep, and we will also post
Thank
a
you.
recording of the webinar on the LF Connectivity site as well.
Thank you.
Thank you, guys.
Thank you, all the panelists and all the attendees for joining us today.
Thank you.
Thanks, folks. Have a great day. Bye.
Thank you. Bye-bye.
Bye-bye.